let's look at the series n equals 1 to infinity of negative 1 to the n root n over 1 plus 2 root n. Okay, so this is kind of nice. They separated the blinker over here on the side, so that makes it easy for us to find b sub n. So I have root n over 1 plus 2 root n. So that's going to be positive. The denominator is bigger than the numerator, so and these are all positive terms, so this looks good. My limit as n goes to infinity of root n over 1 plus 2 root n is equal to 1/2. Uh-oh, that's a problem. That's not equal to 0. Okay, so this means we cannot use AST on here. And so now we need to set this up for the divergence test. So to do the divergence test on this, I'm going to take the limit as n goes to infinity. I have the negative 1 to the n root n over 1 plus 2 root n. So the limit without the blinker is 1/2. The limit with the blinker is going to go positive 1/2, negative 1/2, positive 1/2, negative 1/2, back and forth, back and forth. So this limit does not exist. Okay, and therefore our conclusion is the series n equals 1 to infinity of root n, oops, put the negative 1 to the n in there, 1 plus 2 root n diverges by dt. Okay, so there is my conclusion. Okay, number 3, I have the series n equals 0 to infinity, negative 1 to the n, 2 to the n. So this is certainly a geometric series, a convergent geometric series, but I would like you to show that this converges using AST. So go ahead and pause the video and give that one a try. All right, so hopefully you had some success at showing that that converges using AST, but let's see if we came up with the same kind of idea here. All right, so my b sub n, I'm going to take off that blinker, so I get 1 over 2 to the n. So that's definitely bigger than 0. It's a good start. My limit as n goes to infinity of 1 over 2 to the n equals 0. It's also a good start. And then the last part of this is to show it's decreasing. So if I plug in n equals 0, I get a 1. If I plug in n equals 1, I get a 1/2. If I plug in n equals 2, I get 1 over 2 squared. These are all certainly getting smaller, so I get decreasing here. So I'll stick a sense up here. They have this all nicely organized. Therefore, my series n equals 0 to infinity of negative 1 to the n over 2 to the n converges by AST. All right, so there's our conclusion for number 3. Right, and let's do number 4 together. So number 4 takes a bit of work. It's kind of probably the hardest version of this you would see on a homework assignment, but I do want to show this to you so you can start to learn some of these tricks of the trade, as they call it. So this sine over n pi over 2, sine of n pi over 2 is a little bit confusing. So I want to work out some of these terms so I can kind of see what's going on with my sequence. I think I'm going to line these up here. So I'll do the source of n equals 1, 2, 3, 4, and 5. Okay. So when n equals 1, I have sine of pi over 2. I think I want to do a line that's sine of n pi over 2. So I can figure out what that is. And then I want to do a line that has the terms. So we'll call those the a sub n. The sine of pi over 2 is 1. Sine of 2 pi over 2. So that would be sine of pi. That's a 0. Sine of 3 pi over 2, that's negative 1. Sine of 4 pi over 2 is 0. And then sine of 5 pi over 2 is 1. So I think we can start to see the pattern there. It's going to go 1, 0, negative 1, 0, 1. And our terms are going to look like 1 over 1 factorial. This term doesn't exist since the numerator is 0. This will be negative 1 over 3 factorial. Fourth term doesn't exist. This one will be a positive 1 over a 5 factorial. So I can rewrite this series here as, let's see, what do I want to do? The sum, n equals 1 to infinity. I know that I'm doing the odd numbers in the bottom. So a representation for odds is 2n minus 1. We'll put the factorial on there. So odds are represented by either 2n minus 1 or 2n plus 1. And then these are going positive, negative, positive. So I can do something like negative 1 to the n minus 1. Okay, so now I've rewritten this in a little easier way to interpret what's going on. So let's check our conditions. So b sub n is going to be 1 over 2n minus 1 factorial. And all of those are going to be greater than 0. And the limit as n goes to infinity of 1 over 2n minus 1 factorial is also going to 0. This is getting big very, very fast. And then I need to show it's decreasing. So remember, I stripped off this blinker. So my terms are going to be 1 over 3 factorial, 1 over 5 factorial. And these are getting smaller, so I have decreasing. I have all three of my conditions there. I'm going to put a since out in front of here. And then I'll put a therefore. Okay, and since those guys are equal, so therefore the sum n equals 1 to infinity of negative 1 to the n minus 1 over 2n minus 1 factorial, which is equal to the sum n equals 1 to infinity of sine of n pi over 2 over n factorial, converges by AST. Okay, so this is definitely a little more complicated. I might give you one like that on the homework. Most of them are going to be like the ones you saw earlier, but I do want you to see this trick so you can start to see ways that we can manipulate these series or use these series differently. All right, so when we come back, we're going to look at estimating how close the sum is if we stop at a certain point, so if we use a partial sum.